Hello everyone, I am Piyush Kumar, student of Civil Engineering, Lucknow University. I am here to present seminar on the topic waste to energy solutions and their impacts on sustainable development. The table of contents are introduction, need for waste to energy methods, benefits of waste to energy, challenges of waste to energy, methods of waste to energy in India, case studies, future of waste to energy, and conclusion. So here we go for the introduction. Waste to energy is the process of generating energy from waste materials, burning waste to produce electricity or heat, converting waste into biofuels, reduce the amount of waste sent to the landfills, produces energy, reduces greenhouse gas emissions. Need for waste to energy methods. Every year, world generates more than 2.01 billion tons of trash. About a third of world's waste is being openly dumped or burned. By the year 2050, the amount of rubbish generated annually is expected to increase to 3.4 billion tons. As the rubbish piles up, no number of landfills and recycling programs can keep pace with this growing problem. In order to tackle these problems, we need to have a sustainable and economical method to convert waste to energy. The benefits of waste to energy are: first, reducing landfill waste, minimizes landfill use, addresses limited landfill space, producing energy, converts waste to electricity or heat, provides a sustainable energy source, greenhouse gas reduction, mitigates methane emissions, environmental friendly waste disposal. Circular economy contribution integrates waste into circular systems, promotes sustainable resource management. Fifth, job creation and economy generates employment in waste and energy sectors, stimulates economic growth. Here are challenges of waste to energy. While there are benefits to waste to energy solutions, there are also challenges to consider. These include air pollution and emissions, high capital costs, public perception and opposition, potential for waste diversion from recycling. Methods of waste to energy. There are several waste to energy technologies available, including incineration, gasification, pyrolysis, and anaerobic digestion. Each technology has its own advantages and disadvantages. The choice of technology will depend upon factors such as type and quantity of waste, regulations, and available resources. Gasification is a technological process that can convert any carbonaceous raw material such as coal into fuel gas, also known as synthetic gas. Short form for synthetic gas is known as syngas. Well-known technology with a long market history. Limited implementation due to challenges such as oxidation of hydrocarbons, high levels of CO2 production, emission of pollutants during gasification, low calorific value of synthetic gas produced. Pyrolysis is a thermal decomposition process. In this process, breakdown of organic materials happen at elevated temperatures. It occurs in absence of oxygen or with limited supply of oxygen. Three main products formed after pyrolysis are solid char or biochar, liquid bio-oil, and combustible gases, example hydrogen and methane. Waste to energy by incineration is a technology that takes non-hazardous waste destined for landfill. Waste combustion generates steam for electricity production. This is the schematic diagram of an incineration plant. Anaerobic decomposition is a biological process driven by microbial activity. It takes place in absence of oxygen, distinguishing it from aerobic processes. Microorganisms break down organic materials, converting them into simpler compounds. The main byproducts include biogas and digestate. Anaerobic digestion effectively manages and recycles organic waste, contributing to waste reduction. The process has practical applications in energy generation, via biogas and fertilizer production via digestate. It helps reduce greenhouse gas emissions, particularly methane, contributing to environmental sustainability. Waste to energy in India. Waste generation. India generates over 1.5 lakh metric tons of waste daily. Potential for 200 waste to energy plants. Technology imperative. The need for state of art eco-friendly waste to energy technology meeting environmental norms. Imported technology challenges. Difficulties due to non-segregated waste in India. Promotion of indigenous technology supporting Make in India. This is a bar graph showing predicted municipal solid waste generation, land requirement, and population from 2001 to 2051. Waste to energy developments in India. Renewed private sector interest. Companies like Ramcharan and NTPC invest heavily in waste to energy technology. Niti Aayog's vision for 5.7 gigawatt of waste to energy plants using various waste sources. Ministry of New and Renewable Energy offers a 7.5% interest subsidy and incentives for urban local bodies. Past challenges in waste to energy: inconsistent feedstock supply from urban local bodies, lack of segregation disrupts waste composition, high power generation costs compared to solar and wind energy. Environmental concerns: some countries are moving away from waste to energy incineration due to carbon emissions. Concerns over particulate matter, gaseous pollutants, and carcinogens. Resistance from local residents and environmentalists. Challenges ahead: need for thorough waste composition analysis for each city. Western waste to energy technology requires a higher percentage of non-biodegradable waste. Call to private sector and development banks for investment into more sustainable waste to energy projects. Now we are going to discuss about case studies. There are many case studies from around the world that demonstrate the potential of this approach. Examples include waste to energy facility in Singapore, waste to energy plant in Oslo, Norway, and waste to energy solutions for cleaning dump sites in Delhi. Waste to energy facility in Singapore. Singapore has a population density of 8,592 people per kilometer square. Annual waste generation of Singapore is 7.39 million tons. Incineration facilities. Largest facility for incineration is Tuas South Incineration Plant, also known as TSIP, whose incineration capacity is 3,000 tons per day. Total daily electricity produced by TSIP is 2,688 megawatt hour. Waste to energy efficiency. Tuas one sixth and most land efficient plant of the Singapore, and it is also the most land efficient plant of the world. 90% volume reduction is achieved after incineration. Electricity contribution: 2 to 3% of national electricity demand is met by incineration. Metal recovery: ferrous and non-ferrous metals recovered from ash. Waste disposal process: ash transported to Semakau landfill in covered barges. Final disposal via truck to designated site. Semakau landfill. Pulau Semakau Island is also a green sanctuary and a tourist spot for many tourists. Pulau Semakau landfill space will run out by 2035. Figure 4 shows boat carrying a covered barge in which we used to carry ash after incineration from the incineration plants. And figure 5 shows aerial view of Pulau Semakau Island. The conclusion we can draw from the case study of Singapore waste to energy plant is efficient waste management, energy generation, and environmental consideration play a crucial role in Singapore's sustainable development. Action is required for further waste disposal challenges. Waste to energy plant in Oslo, Norway. In Norway, waste is segregated in different bags, such as green bags for food waste, blue bags for plastic waste, and other colors for paper, glass, and other miscellaneous wastes. Green bags are sent to biogas plant for biogas gas and biofertilizer. Blue bags are sent to recycling facility for new plastic. Other waste is sent to incineration plant for generation of energy. Incineration provides heat for Oslo district heating system. Oslo incineration plant has capacity of 410,000 tons of waste annually. Oslo also imports 45,000 tons of waste from United Kingdom. Europe dumps 150 million tons of waste in landfill yearly. Potential for energy generation from waste can be seen in European countries. European countries pay Norway for waste disposal services. Norway's waste management model emphasizes segregation, recycling, and energy recovery, contributing to a sustainable and economically viable solution. Oslo's capacity, waste imports, and European practices underscore the global potential for waste to energy initiatives. Revitalizing Delhi waste to energy solution for cleaning dump sites. Delhi has three major dump sites, namely Gazipur, Okhla, and Bhalswa. Area covered by these dump sites is 200 acres, holding 28 million tons of legacy waste. Legacy waste comprises of inert waste, construction and demolition waste, and segregated combustible fraction. Inert waste is being utilized in national highway projects. Construction and demolition waste is used for manufacturing of bricks and tiles, and segregated combustible fraction is used by cement and thermal industries as RDF. RDF is known as refuse dry fuel. Okhla dump site cleanup progress. Okhla dump site cleanup was initiated in November 2022. Achievements: 12 lakh tons segregated and repurposed. Gazipur's impact on infrastructure. Delhi Ring Road UR2 utilized 30 lakh metric tons of inert waste, reducing height by 7 meters of Gazipur dump site. Waste utilization in highway construction. Inert waste contributes 50% to highway construction. Collaboration for efficient waste utilization is very important. Cleaning timeline. Projection. Okhla Bhalswa by December 2023. Gazipur by March 2024. Challenge. Limited machinery hinders faster waste segregation. Only 30% waste is cleared till now December 2023. Background: Delhi faced massive garbage dump reaching over 60-meter tall. Introduction of waste to energy plants as a solution. Gazipur Waste to Energy Plant, established in 2011, processes 2,000 tons of waste per day, generates 12 megawatt of power and 127 tons of fuel, contributes to India's 40% fossil fuel based energy goal by 2030. Air pollution control measures. Adherence to European Industrial Emissions Directive, stringent pollution control devices implemented. Central Pollution Control Board report submitted to the National Green Tribunal and Supreme Court reveals toxic emissions from waste to energy plants in Okhla, Bhawana and Gazipur areas. Chief pollutants are dioxins, furans and PM2.5 exceeding permissible limits. Health implications. PM2.5 linked to cardiovascular diseases, lung cancer and respiratory disorders. Dioxins and furans generated by incineration among the most toxic substances known. Conclusion: the Gazipur waste to energy plant, while contributing to energy goals, faces challenges highlighted by Central Pollution Control Board report. Balancing energy generation with environmental and health concerns is crucial for waste to energy initiatives in Delhi. Future of waste to energy: a path to sustainability. Unlocking sustainable potential. Waste to energy solutions offer a promising path toward a more sustainable future. Advancements in technology and cost reduction make these solutions increasingly viable and scalable. Key factors for future: ongoing technological advancements, constant improvements in waste to energy technology enhance efficiency and reduce environmental impact. Sustainable Development Goals. Waste to energy aligns with key sustainable development goals. Goal 7: affordable and clean energy. Goal 11: sustainable cities and communities. Goal 12: responsible consumption and production. Goal 13: climate action. Environmental benefits. reduces landfill reliance and methane emissions, mitigates environmental pollution, generates clean, renewable energy. Economic and social impacts. Economic growth. Waste to energy projects create jobs, stimulate local economies, and enhance energy security. Resource recovery. This approach promotes recycling and reduces the need for raw material extraction. Public health. Waste to energy reduces waste related health risks. Urban environment. Efficient waste management and reduced landfill reliance result in cleaner, more attractive urban environments. Conclusion. Promising path forward. Waste to energy is a promising path towards a sustainable future. Global sustainability. It aligns with sustainable development goals and contributes to global sustainability agenda. Continuous advancements. Ongoing technological improvements makes waste to energy more viable and environmentally friendly. Economic and social benefits. It brings economic growth, resource recovery, improved public health, and cleaner urban environments. Environmental responsibility. Waste to energy reduces pollution, methane emissions, and generates clean, renewable energy. A cleaner future. Waste to energy has potential to transform waste management and energy generation for a more sustainable world. Everyone.